Hello, how's it going? Today we're going to talk about debugging quickly, hopefully. There's a lot of great principles to debugging that can help you, and we'll go over those. If I go to the course website and I can download my IPYNB file and open that up, some specific debugging principles that I've found helpful in the 20 years I've been writing code is to start simple. Don't bite off more than you can chew and write 20 lines of code without testing. So start with a simple task and then test it, make sure that's working, and then build out complexity. Make sure you comment your code or name variables in a way. So instead of putting Z as a variable or G, explain what the variable is in the variable name. Like G, if that's gravity, sometimes that's obvious it's G, but other variables maybe not, so you can write out the name. Test often. Test often means try to do this simple code in small pieces and then run it and make sure it's doing what you think it is, and then add a new feature, make sure that feature is working. Print statements are very helpful. You can add a print statement, so anytime you see something new, like maybe a double, like for instance, if you haven't seen this before in a piece of code and you got some variables in there, like, I don't know what this is doing. Well, you can substitute variables and just see what is it doing. Like, oh, that's the floor operator. Or any other new thing that you see, a new feature, you can try to use it on its own. You can go to the documentation in Python, so I can go Python documentation, and you can search for the modulus operator, for instance, and you can read about how that's done. Other options are, of course, to use AI tools like Gemini or ChatGPT. So yeah, those, you can Google the warning. So we'll talk about what kind of different bug types there are next, but simplifying your code and checking your answers, doing it different ways. This is big for logical errors. So syntax errors are errors that you mistype. You put a colon instead of a semicolon, or you put the wrong name for the package. And Python's really good at telling you what that is, and so it'll point to the line and tell you how to fix it or what's wrong. Execution errors are not syntax errors per se, but when you run the code, it crashes. So maybe you're referring to a bad array call, or you've assigned variables incorrectly. The newer versions of Python have checks for this, and will give you almost like a syntax error for some of these. I've noticed as Python's grown in popularity and improved. So the logical errors are hardest to find, and your code runs fine and you think it's doing what you thought you told it to do, but it's not. It gives you the wrong answer. They can be hard to locate these, and so you kind of have to break it up and do it line by line or systematically, tracking through how the code is running. So we'll run some examples here with the Holland equation for the friction factor for finding the friction loss in a pipe. Here's that Holland equation, and there's some key pieces of information in terms of how the Reynolds number, where this is valid. So you may not have seen this yet, but you're in fluids class, or soon will be, and this Reynolds number kind of defines flow characteristics of the fluid. There's the roughness of the pipe. If it's got marks in it, or if it's really smooth, and then D is the diameter of the pipe. You don't really need to know what the Reynolds number is right here, but just to know it's a variable. And here's the syntax area syntax error. So it says, hey, there's no numpy, pi. Oh yeah, I gotta do numpy, y. And there's not matplotlib, it's matplotlib. So correct that. And then this one, hey, how do we refer to arrays? So this is an array, right? So if we wanted to print that out, for example, quickly, the Reynolds number, hey, that's an array. So how do we reference arrays? Oh, it's not with parentheses, it's with brackets. So let's correct that. Oh, good. There we go. I got the first value in the array there. If I print this, and then there's the first 10 entries and the last 10 with my array slicing from several lectures ago. And let's see if we can define our function and call it. And it got multiple arguments for RE. So this one is a little harder to find. So it's highlighting it right here. So what is this saying? Friction factor is a function of Reynolds number and E over D. So the roughness divided by the diameter. Oh, well, yeah, I got 2 Reynolds because this 4 is rifling through each of the Reynolds number. So yeah, I'm not going to want this second one here. So now I got this is an array of friction factors for each of my Reynolds numbers. Now I'm going to see if I can plot that, saying FFD is not defined. Oh, let's typed an extra character in, but there is my Holland friction factor. So there's assert statements as well. These are down here, we'll go over. But the debugger, there are many code, IDEs, VS Code, and others have debuggers that you can step through your code and almost mouse over it, and it'll tell you what the actual value is right then. That can be very helpful for logical errors in code. See, we got some more syntax errors here. Transpose. I'm trying to do that manually here given this array. So it's saying setting an array element with a sequence. So this is a logical or runtime error that this isn't going to work as it's programmed there. I'm not going to go through how to fix it, but you should understand transpose and maybe how to do it manually instead of having the code transpose it. But this is a check to see if you did it right, because T remembers transpose and it'll do it for you. And maybe here's some more examples. This is looking like, oh, you can't assign a function call to an array. So you may want to change these, for instance, to brackets instead of parentheses. Here's a third one. SymPy has an equation solver. So this SymPy package, I can enable printing, set up a variable, give it an equation. This is a third order, a cubic equation. And I can solve that, and it will give me a symbolic equation. This roots eval f. There's a problem there. It doesn't have an attribute of eval f. So if I just comment that out, there are my roots. So there's right here's 1, 2, and then the third one right there for this equation. So that's pretty cool. It symbolically solves that. And just for kicks, let's just do x squared, like the cubic, or no, the quadratic equation. See that one? And there's our two roots for that one. So you get the same answer for the quadratic equation. And maybe we add a fifth one, see what it does. It says, yeah, you're going to have to get roots for each of these. So, it did the fourth order. That SymPy can be helpful. Assert statements, you can say things like this. If the type n, when you feed a factorial, is, you can say make sure it's an integer and that it's greater than 0. Otherwise, say, hey, this needs to be an integer or greater than 0 for to do a factorial. So that can be done with like this. Somebody feeds a hello. Well, you can't do the factorial of hello, and it gives you the error. If you don't have this assert statement right here, what happens? This greater, it just gives you a slightly different error, but it tells you where approximately the error is. It's trying to do this operation with a string. So these assert statements can be very helpful when you're building code for others to interact with rather than the code you run yourself. And using a debugger, we won't go through that, but God lives and loves us. Hope you have a great day.